Okay, so last time I told you how to formulate a dynamic problem, and it just comes by changing the load vector on the right hand side, which is because of static loads that can be generalized to take into account the inertial forces. Inertial, keep in mind that inertial forces act opposite the direction of motion. So, M matrix, the mass matrix, and mass matrix is defined by integral what? N transpose rho is the mass density n, n is the shape function matrix dV. dV is standard. In one dimension it will be area of cross section into length, in two dimension it will be thickness into area, in three dimension it will be volume as such. So, that is how it. So, you have to. Now, many times you also have whenever dynamic forces act on the body, there is also what is called damping. In addition to inertial forces, you also have, whenever body is in motion, you also have damped. Now, damping is very difficult to find out what is the so damping. This I will not take today, but I will just quickly close it. Damping effect. Now, the behavior or the action of damping also is similar to inertial forces. Damping also dampens the motion. So, it also acts on the body if x, y, z are the positive directions. So, it will be. So, there is something called coefficient of damping C, which we denote it by C, just like mass density we call it coefficient of damping C, coefficient of damping per unit volume. How to find out this coefficient? I think we will have to refer to some books on dynamics. It is not easy. Damping parameters are very difficult to find out. It depends upon the type of structure, material used in the structure. There are so many, but still it is worth knowing about damping. So, damping is not easy, and therefore, Rayleigh, R-A-L-E-I-G-H, Rayleigh, Lord Rayleigh, he gave a simple formula that whenever damping, Rayleigh gave a simple formula that similar to your mass matrix, damping will produce or will give rise to, instead of mass matrix, a damping matrix C, and C can be this damping matrix. Sign will also be same as that of mass damping matrix. This can be written as alpha times mass matrix plus beta times, it is a combination of stiffness and mass of the body or particles, whatever you want to say. These are the two coefficients alpha which are found out experimentally. So, these are coefficients to be found out, to be evaluated. So, it is not easy, evaluated experimentally for different types of structures and different structure type and environment in which they are situated, and environment V. Generally, and these coefficients, if you see our book by, which is the famous book on dynamics of structures, Anil Chopra. Okay, Anil Chopra has replaced our Clough and Penzian. Before, see, the teacher of A.K. Chopra, A.K. Chopra was Clough and Penzian. They were the same university. Now A.K. Chopra has written another book, so perhaps it should be better than the previous one. Otherwise, Clough and Penzian was the classic reference book. So if you see there, they have given tabulated these values for different types of structures. Generally, beta is a very small, it is 0 something. Beta is a very small value, and therefore, if beta is very small value, beta is small generally for most of the. So if beta is small, then C is approximated simply as alpha times m. So and alpha is tabulated, alpha is known, these are given in the coefficients, these coefficients are experimentally evaluated, and these are, so alpha times m. So that means the form of C will be same as that of m, except that there will be one coefficient alpha, nothing else. So whenever you have damping, that means your dynamic equation, just like single, I think those of you who have done this, single mass and then damper. How do you yes, this is K, this is C. This diagram you must have seen. Acha, mass is not there. Where is mass? Mass has to be somewhere. Is it okay? M. So mass, of course, you have to have, so that it does not fall on the floor. So you have to have some roller, but doesn't matter. This is, so this one, the equation, this one is written as mx if this direction is x you are measuring. So single, for single degree freedom, you must be remembering Cx dot. Damping is always proportional to velocity. So damping is proportional to velocity. So this will be plus Kx equal to Ft. So this is for single DOF. And now we have done finite elements, we are dealing with multi-degree freedom system, general. So ours one will be m d double dot plus c d dot plus k. So this is the most general equation of dynamics that you can think of. A second order ordinary differential equation which is coupled. So this is the coupled second order ordinary differential equation system for what? For damped motion of any body, for damped, that damping in damped motion of any body having n degrees of freedom, because everything this d having So, because D means D is having lot of something like this. Okay, so that means this is a in finite element when you are dealing with dynamics, then in addition to this is statics, then this will not be function of t. The moment it becomes dynamics, without damping it will be this, with damping it will be this, and this does not exist for dynamic problem, for a structural dynamic problem, but then in heat transfer problem this exists. Heat, you have first order, you know, the equation which governs the behavior of heat transfer in a body is only first order derivative. So you also have this you get transient dynamic behavior of any when you want to do thermal problem. So you also get first order. So there you get first order transient problem, first order ordinary differential equation, and while in dynamics of structures we get second order, and it can be with or without, and you know how to form the various matrices. So I will stop here, and if time permits I will tell you how to deal with dynamic problems. Okay, today now then I will take, let us review. We have done this see, this is shape functions or interpolation function, the function which is assumed for the behavior of any parameter within the element is called interpolation function, and same function is another, because there is a particular way in which we write, because the same function is written in a particular manner, so it becomes shape function. So this is the most important thing in finite element. So I will just review it quickly. The basic idea of finite element method is piecewise. Is it visible here? Is piecewise approximation. Piecewise total domain is discretized into smaller parts. So piecewise approximation, that is the solution of a complicated domain is obtained by dividing the solution domain omega into small subdomains or regions, and these regions are called finite element or omega e. Clear? And approximating the solution over each sub region by a simple function. So I have been telling you that total domain I cannot use the function. It is very difficult to assume a function variation of function in the entire system, but yes, in a smaller zone certainly I can take a how. So that is what is the basic philosophy of. Then next, no reasons, no questions will be. The functions used to represent the behavior of the solution within an element are called approximating. There are number of ways. This again I have been telling you. Approximating, interpolation. Interpolation means interpolate from node to node from over the element. Our mathematicians call it basis function, and then we write the same interpolation function in a particular form, and then it becomes a shape function. Okay. If you write u equal to a plus bx, it is interpolation function, and if you write u equal to n1 into u1 plus n2 into u2, now n1 n2 will be the shape functions, but then the degree of these shape functions will be same as that of a plus bx. Okay, degree does not change. Only thing, the manner or the method, we are not writing in undetermined coefficients in the form of a and b, but we are writing in terms of nodal values. Why do you write nodal values? Because it means it is a physical quantity. I am concentrating on nodes, so I write it in terms of nodal, and then these coefficients have some physical meaning. n1 into ni's. So, shape is okay. Now, polynomials are widely used as shape functions due to following reasons. Why? What is the one is easier to perform differentiation or integration with polynomial. Clear? Then we also know that solution accuracy is improved by increasing the degree of the polynomial. We can start with linear, quadratic, cubic variation, whatever it is. So, these are some very basic properties of shape function. So, quickly I will just, then these are the common polynomials, and I have already covered this. One dimension 2a plus, I mean, instead of calling a plus bx, I have written here a1 plus a2. In 2 dimension it will be this, in 3 dimension it will be xyz, okay, minimum, and all this come from the, from what? From the Pascal triangle, or it is also called Pascal tetrahedron in 3 dimension. I have drawn it here, I think it should be visible. This is triangle, see, and tetrahedron means 3 legs, stool. You make a stool and then show this. So, this you have to ensure that all the terms. So, this one is linear. Quadratic means I have told you how it is to be taken, and why do you take quadratic means, and there was one more, okay, quadratic. These terms are taken such that our this basis function or interpolation function is isotropic. It must be symmetric. You don't take x square x cube, leaving y equal to only y square. If it is y square, you must take y square, x square and xy from the Pascal triangle or Pascal tetrahedron. And same thing, supposing you want to start with the cubic function. So, the first will be this in 1 dimension, in 2 dimension it will have. So, that means you need 4 constants, 4 nodes. That is why the basic element is a tetrahedron in 3 dimension. Basic element is a tetrahedron, 4 noded, 4 faces. Basic element here, because there should be as many coefficients as there are nodes. No. How many? 3. Yes. Linear, as many degrees of freedom. Here in 3 dimension, how many? No. Here you see. What do you mean by quadratic? You see, this is the linear word, tetrahedron, only the nodal values, 3, 4 nodes, so 4 constants are there. Now, here in 3 dimension quadratic, I want the variation to be not linear but quadratic. Then there are 10 nodes are required. You need 10 nodes to represent that. So, this also gives you how many nodes in the element should be there. So, kindly do some practice, and same thing if you want a cubic variation within the element, then the basis, the first in 1 dimension will be this, and in 3 dimension there must be 20 nodes, 20 degrees of freedom. So, this one is okay. Now, choice, this is important in finite element, or because this is when somebody asks you, I mean, these are some common questions when any interviewer asks the student, if he is interviewing him or her on finite element. So, the interpolation polynomial should satisfy the convergence criteria, and I have been telling you one thing very clear, that the variable field, that means your polynomial, should be complete. What is the meaning of complete? And continuous within the element. Any function that we use within the element, it must be complete. What is the meaning of completeness? Continuous is all right, differentiable, continuous. complete, it should contain all the requisite terms in the Pascal triangle. Complete, don't leave out any term, you know. If you want a triangle, there must be a1 plus a2x plus a3y, x and y, and 1xy also, a4xy. Is it okay? If it is in 2 dimension. So, complete, the completeness also is important. Then uniform or constant state, that is, I have been telling that triangle meets the requirement, that is strain is constant, CST element. So, uniform or constant state of the variable and its derivatives up to the highest order that is appearing in the integral function. Where does this integral function come? I have not made it, but you tell me. Integral function is when we write down the functional pi, energy, there is an integral, is it not? When we do from energy, the integral, what does enter into integral? It is the strain term, and strain normally is the first derivative. So, if displacement is linear, first derivative will be constant. Okay. So, constant state should be, see, constant uniform state must be, and then the next one it says up to the highest order appearing in the integral function should have representation in phi as delta or as the area or volume of the element tends to 0. This I have been telling, that in the limit you must get constant states of strain. Constant, that means constant state of what? First derivative. It is a first derivative. Strain is given by first derivative, du by dx, first derivative. So, if u is linear, it will be constant state. So, that is a criterion. So, your CST, that is why CST element meets this criteria without difficulty. Then the second one is, that is important.
So if it's not linear, then it won't be constant, and hence if we use quadratic, it won't be linear, so this condition won't be satisfied.
Yes, yes. No, not necessarily. What I am saying, not all elements satisfy this, but as the size of the element tends to 0, at least ensure that it is becoming constant. So, even if it is quadratic, as the size reduces, you ensure that it has terms that make it constant within the element. Okay. So, that one, the first derivative should be as far as, then it has requisite property of a proper shape function. Convergence criteria is met. I will tell you when we, you know, I don't want to discuss now. I just want to go through, and then because I want to cover something, I will take it up little later. Then next one is field variable, that means u, v, w, r, phi, temperature. The derivative up to one order less than the highest derivative in the integral functional. Now, this you may not have noted because the way we have done, but in the integral you have strain term multiplied by E term, and again strain term which comes, you know, that is why you get B transpose EB, is it not? That is the reason why you get that. So, it is the strain term. Now, strain is first derivative. Now, the requirement is that one derivative less than the first derivative, means the basic variable itself. You should ensure that the basic variable is continuous within the element, and also, yes, across the element. One derivative less than. Okay, so if now here we are dealing, so far I think we have dealt only with the first derivative, luckily, because that is the simplest. But there will be problem, you know, later on we are going to go to a, in next class I will go to plates. There you will be dealing with second derivative. In the integral there will be second derivative. So, one order less will be first derivative. So, that will ensure, you have to ensure that first derivative also is continuous across the element, and that is very difficult to meet. I can make first derivative continuous within the element, but not across the element, first derivative. So, there are elements which do not meet all the requirements. So, this you have to see that field variable and highest derivative, this one integral function must be continuous within the element at element boundaries. Then you have perfection. Then your finite element formulation is perfect. But in this world, everything is not perfect. There will be a situation where your element will meet only part of these requirements. So, that is why you don't get that element will not be a reliable element. Okay, that is why we try to see that it meets. So, this is a requirement. Then have you seen anywhere this term C0 element or C1 element while going through the book? Did you C0, C1. So far we have dealt in our course what I call C0 element. What is C0 element? C0 element is one where we are dealing with continuity of only the basic variable. U, V, W, basic variable only, not the first derivative or second derivative, continuity within the element and across the element boundary and across the element boundaries. Okay, only basic variable. So, that is easy. So, such elements or such formulations which requires only continuity of the basic parameter or basic variable which are your nodal parameters, those are called C0, because there is no derivative. First derivative means it becomes C1 continuity. So, we call it C0 continuous element. So, this is a different way of telling the same thing. It is a C0 continuous. So, whatever we have done so far is C0 continuity requirement or C0 continuous element. We have dealt with only C0 continuous element. So, elasticity problem C0, axial rod problem C0, because in the strain, and what is the test? In the strain energy term, you should have only first derivative of displacement, because continuity, in order that you can evaluate the integral, if it is a first derivative, the requirement is that my u must be continuous within the element and across the boundary. Okay. So, such formulations are called C0 formulations or C0 element. So, this is for your information. I mean, very simple and clear definition. In the strain energy expression, if you have first derivative of your basic variable parameter, anything, it can be temperature, displacement, velocity, and if that happens to be your nodal parameter, then if it is only first derivative, that formulation will be C0, because you will be dealing with only continuity of those parameters within the element and not its first derivative or second derivative. Then other thing which I have been telling you, that I have just written here again, the interpolation polynomial should be isotropic. What is the meaning of isotropic? You should have x and y term similar, not one side x and other side y square. You must take isotropic, behavior must be, element must be isotropic. So, that property is called isotropic element. Then this AIs means generalized, that is ABC coefficients should be equal to the number of nodal degrees of freedom. This also by now you must have realized. There is some relationship between ABC and the number of degrees of, because you can put boundary conditions only that many. So, degrees of freedom. Okay. So, this is now I have already told you about, and started last time about some idea about numerical integration. Why numerical integration is needed? Okay. Please just tell me whether this is visible clearly. Is it? Is okay? All right. Then it is okay. Then I need not rewrite, because it is faint on my. Okay. Now numerical integration I told you last time. Why do you need numerical integration? What was the idea? Why not always do with hand integration? I think that is when finite element is started, first 5-6 years people used to do only, but in those days people were using simple elements, only linear, bilinear and trilinear for 1, 2 and 3 direction. Later on this thing came, no, we should use you should use higher degree polynomial, quadratic element, cubic element. Why? Because we will improve the behavior of the element by taking that. And the moment you take quadratic, cubic, then the integration becomes difficult, tedious. Okay, integration will become tedious. So, and the other one is that a need was felt to do all the calculations in a coordinate system which is local coordinate. Instead of doing the global coordinate, because you will have to do x1 to x2 integration, x2 to x3, you have to keep track of all this. Instead of that, we will do integration in a defined local coordinate and we will relate the local coordinate to the global coordinate. This, I think this I have already shown you in the case of truss member, but in general this is local and global concept is done even here. So, and then I told you that instead of doing integration from x1 to x2, if you can do the integration, make the x1, x2 non-dimensional, makes your x coordinate non-dimensional by dividing it by the length, and see that integration starts from -1 to +1. And the reason is because in the numerical analysis book there are some formulae which are already existing. For any function from -1 to +1 can be integrated using those formulae. Somebody has already worked, done the work for you. You simply take the coefficient formula and then integral will come in one step. If it can be from -1 to +1, and that formula is due to Gauss, Gauss. So Gauss formula. So Gauss entered into finite element method because of this. Okay. So local coordinate, non-dimensional coordinate. Now let us see local coordinate. There are many things. Now this is a simple rod. This is the global coordinate is x, starting from here. You are okay at the back. What is? You are comfortable? Or you should come in the front, there are so many seats. Okay, so x1, x2 are the two nodes whose the coordinates. Now I want to devise a non-dimensional coordinate, and with the mind with the idea in my mind that let my coordinate starts from -1 to +1. So what I do, I put the center of the element as origin of a new system of coordinate. I take a non-dimensional coordinate which I denote by psi, like this, psi. Psi is a non-dimensional coordinate. So psi starts from here, positive on this side, negative on this side. So psi equal to, I want psi equal to -1 here, +1 here. I want. This is the length of the element. So psi is going from -1 to +1. We call x as a global coordinate and psi as the non-dimensional. I don't know, there are so many names people call it. I call it by non-dimensional coordinate. Okay, non-dimensional, natural, normal, these are very so many coordinate. Now, how do you transform the local to global? There must exist a relationship. The relationship is, if I take psi, multiply, make it dimensional by multiplying by L by 2, length of the element, x2 minus x1 by 2. What is L? L equal to x2 minus x1. What is the value of L? No, just x2 minus x1, difference in the two coordinate. So this is this. Now you take any point. How I have done this? How did I get this? See, psi, you take this point, let us say at this point, from here to here. So it is a psi, this point how to L by 2, I am multiplying, and this one is x. From here to here is x, because this point is P. P is having x and P is also having a coordinate psi. P can be defined, Acha, sorry, you cannot see. I am sorry. Now you can see. P can have, because the same point P is defined by two coordinate, x and psi. Now I want to develop the relationship. So relationship is developed by psi multiplied by L by 2, and from here to here is how much distance? X minus this distance is how much? x1 plus x2 by 2. So I have just done this. So now this is equal to this. Why did I multiply psi into L by 2? Because psi is varying from here to here, this length is L by 2. Psi is going from here to here, positive, na? So this is L by 2. So this is, and from here I get a x as this, then I have substituted x1, x2, and then I have rearranged the same thing. I have taken now x1 coefficient, x2 coefficient. This is very interesting way of writing the same thing. This is psi. So psi becomes the coefficient of x1 and x2. Then it is very interestingly, this is the behavior of 1 by 2 into 1 minus psi is what? If you plot this in the element, its value is, when psi equal to +1, it is 0. Plus 1, yes, psi equal to +1. Yes, okay. Yes, psi equal to +1 means you are here, it is 0. When psi equal to -1, then this is equal to 1. In between it is a linear function. So it is similar to this triangle, shape function for node number 1. So I am writing the same shape, so that is why I have written now this shape function n1, except that now n1 is being written in psi, as a function of psi, not as a function of x, but otherwise it is the same. So n1 psi multiplied by x1. Similarly, the behavior of this coefficient is similar to n2, except that this represent, because see, this is equal to psi equal to -1, this is 0. At this point it is 0. At this point it is 0. When you are here at the node number 2, then it is node number 2, it is equal to 1, because 1 plus 1 divided by 2, 1. So this is like shape function for node number 2. So it is n2, and very interestingly now x is represented as n1 psi into x1, coordinate x1, into n2. So this is a new representation, into n2 psi into x2. So I can write x, left hand side is x, So we were here. So this is a very important formula that which defines the geometry of the element in terms of nodal values and shape functions which are defined locally. These shape functions are not defined globally, but they are functions of local coordinate psi, non-dimensional, which varies only from -1 to +1. So this I have written here, that the above establishes a unique relationship between x and psi. X is global, psi is local. Now we already, now I'm going back to, so this is a, this happened, this is a very new result, that people. Now let the global bar displacement be expressed in the same way as, now let us express displacement also in terms of local coordinate. How does it matter? So I am saying u function of psi within the element as ni psi ui. That means I am defining my u locally within the element, not in x but in psi coordinate. Now can somebody find out what will be the strain at any point psi in local coordinate? See, u now I am assuming in the same way as this. Is it okay or not? This relationship is okay? Yes, within the element it goes, from this value is unity 0, this is okay. So I can now find out, strain. For example, I can have strain which is a function of psi. Let me find out strain, not in, but I will as du which is a function of psi by d psi. Locally I am finding out strain in local coordinate. Normally it is what? Psi strain is in global coordinate will be du by dx. Now I am finding out locally strain is equal to this. And what is du by d psi? Du by d psi, can somebody tell me? Yes, du by d psi. What is u? You just take u psi is equal to n1 psi into u1 plus n2 psi into u2. So this du by d psi is equal to dn1 by d psi u1 and what is this? This value comes out to be, of course, n1 is 1/2. What is n1? N1 is n1 psi locally is 1/2 1 minus psi n2 1 plus psi. So you just take what is dn1 by d psi -1, -1 half, -half. So this one is -half u1 and dn2 by d psi plus half. So it is u2 minus u1 by 2. What is this? Normally strain as a function of, because in the global coordinate, r, is it okay, is equal to du by dx, if you want. Now that can be written as, by chain rule, du by d psi by dx, and du by d psi, just now we have got u2 minus u1 by 2. What is this? D psi by dx. I don't have psi as a function of x. I have a relationship of x as a function of psi, not the inverse. But then let me find out x as a function of psi and then invert it, then do it reverse. So here we have, I will just write it here. See, some silence please at the end, last rows, please do not talk. What we have is, we also have x as n1 psi. Now everything, all n1 is defined as n1, n2, they are defined in terms of psi into x2, and therefore dx by d psi will be dn1 d psi x1 plus dn2 r. This is equal to minus, just now we have done this, x1 plus 1/2 x2, and that is, this is equal to x2 minus x1 by 2. Similar form, du by dx u2 minus u1 by 2, this one is x2 minus x1 by. Nodal values will be nodal values whether it is a local coordinate or global coordinate. u1, u2, these are values at the nodes. These have nothing to do with coordinates. Similarly x1, x2. So we have got both, and therefore, I mean, just to check, I want to, so we were there. If you want to find out this as a function of, in terms of x, then it is du by d psi in local coordinate, derivative of u with respect to psi, because you have defined u in terms of psi now, multiplied by this. So I will say it will be 1 divided by dx by d psi. And therefore this is equal to 1 divided by dx by x2 minus x1 by 2 into du by d psi. Yes, what is x2 minus x1 divided by 2? L by 2. Very good. So if you want to find out strain in the global coordinate, so you find out strain in the local coordinate. This is strain in the local coordinate. Du by d psi is what? Strain in local coordinate, which I explained to you here. Strain in the local coordinate equal to u2 minus u1 by 2. So in general, strain in the local coordinate multiplied by a parameter, this x. This is L by 2. So 1 divided by L by 2 length into du by d psi, and I can only tell you that left hand side is du by dx. So derivative of u with respect to x is Can we write this? Can you please find out so we compute, so in this formulation what we do, we compute strain in the local coordinate. Not, now we have got an idea, yes, this is global coordinate. If I take this derivative, which is the strain, is related to the strain in local coordinate, but then I have to multiply by L by 2, half the length of the element. This is the length of the element, this is minus 1, this is plus 1, and so this is L by 2. Then it gets transformed into, okay, so this is the transformation. How should we go about it? Strain, okay, yeah. So strain psi du by d psi or d upon d psi. See, I cannot help myself. So n1 psi u1 plus n2 psi u2 or I can write it like this. Horizontal matrix, I am writing so many times this as a function of psi multiplied by u1. So what is this matrix? Tell me. This is psi, this is strain at any point within the element in local coordinate at a point P. Psi I have written clearly here. Is it okay or not? This is equal to this. What is this matrix then I should call? B. But then this one is your B as a function of psi. This is B in a local coordinate. B has been obtained in local coordinate. B means derivative of shape function has been obtained, and then this is your D. And how do you get energy? Strain matrix is important. How do you get energy? Energy expression. Normally we do this, pi is equal to u minus w. U is half this, what? Strain, all the, if there are all the 6 strains, all the stresses multiplied by V minus work done by what? So what will do work when Yes, UVW. You should be very clear. Normally, how should we write this? This term W should be written as what? They will do work on what? If UVW are the displacements, or U is the so it will something like this: UVW multiplied by Px, Py, Pz per unit volume multiplied by dV. So that work done by external forces distributed per unit volume. So something, and what will be this? What will you call this? U transpose. What will you call this? P. I think this expression I have given. So your energy expression is always strain transpose sigma into dV. So just now we have seen something. Yes, we would like to compute these energies of the element. Whether you do in global coordinate or local coordinate, energy will remain the same. It will not depend upon. So why not compute in psi coordinate? This one. This is all is the crux of the matter. So these two energies are computed in local coordinate. Once you do in local coordinate, it will be equal to pi of the element, local, I am just putting now instead of this energy, equal to strain energy of the element minus W of element. These are all we are doing for element only. Okay. So then that will be equal to this strain. Strain is, we just now we got it here, B psi into D. Yes, in local. Here. B psi into D is okay, strain. Then this one will be transpose करना पड़ेगा, otherwise there will be problem. Transpose, okay, transpose कर देते हैं, and then E, and then again B, because again is strain, so again B. Yes, and this transpose, see this transpose, this total transpose into dV. dV is what? dV is equal to A into area of cross section. Let us say we are doing for the rod, area of cross section into dx. Okay, d, okay, d psi. All right. Yes, okay, area of cross section into d psi. So this will give me, this will compute me the strain energy in minus, of course, minus this quantity, minus the, and that is very simple, n times. Now here this is again local coordinate. This will be, I think, where is U? U was here. Silence please. U is only thing, U is defined in local coordinate. So U transpose, it says U transpose P. So what is U? u equal to n times d, n times d. So what is n? N times n of psi, so it is n times d, so that is d transpose, n transpose, n transpose. So n transpose looks like vertical or horizontal? Original n matrix is defined horizontally, so it is n transpose times p, and again dv. dv will be a times d psi. So you compute this all locally, and this will be from -1 to +1, -1 to +1. क्या हो गया? And this is n transpose. So this is okay. So this is done locally, and then how do you transform this to globally? And global, the only change that will occur, wherever, listen, wherever dx is there, dx is given by what? dx and psi. What is the relationship between dx and psi? It is L by 2 times d psi, and L by 2 is L by 2 into d psi is dx. Yes or no? Yes, it is. X equal to. So wherever dx is there, you will have to multiply by L by 2. Now this one, in one dimension, there is something called Jacobian in 2 dimension and 3 dimension, which transforms the one coordinate to another coordinate. You know, Jacobian. So this is nothing but Jacobian. In 1 dimension. And it is denoted by J, Jacobian. So we also write this is J times, J is a number and J has to be a number. So in 1 dimension it is already L by 2. In 2 dimension it will not be a scalar quantity, it will be a matrix, and so we write it in determinant like this. In 1 dimension it is easy to express, but we write it J determinant because that will give me the number. Yes, sign this. So this is one relationship that will be, so wherever dx is there, you will have to change to this in order to get the quantities in the global coordinate system. Otherwise everything will be. So please do this. Please formulate as an example the same rod element, 2-noded rod element. We have done it in global coordinate system, x coordinate. That time it was only x. Now please do it using local coordinate system. Local coordinate system. And even if you do local coordinate system, the final result should be same. So kindly complete, do this exercise, and you will be, because it will require a lot of steps initially, and then you finally formalize. Okay. So this is called isoparametric formulation, wherein both x and u are defined by the same shape functions.